In the final months of the year 946, a mountain disappeared from the map, not gradually, not quietly. In one catastrophic instant, it exploded with such violence that volcanic ash reached Japan, over 1,000 kilometers away. Witnesses, had they existed, would have seen columns of fire and smoke rising to unimaginable heights, 30 kilometers above the surface, higher than 3 Mount Everests stacked upon each other. The sound would have been heard across entire kingdoms. The sky would have darkened for days, perhaps weeks, and then silence. Where once stood a majestic peak, only an open wound remained in the Earth's crust. A caldera 5 kilometers wide, 850 meters deep, an abyss carved by unimaginable forces. This was the Millennium Eruption, one of the most powerful volcanic events of the last 10,000 years. More violent than Krakatoa. Nearly half the force of the terrible Tambora that would darken the world centuries later. And it happened in a place where, geologically speaking, there should be no volcano at all. This is Changbaishan, or Paektu, as it's known in Korea. Heaven Mountain, the mountain of the gods, and its story defies everything we know about volcanoes. Because you see, most of Earth's great volcanoes follow a predictable pattern. They are born at the edges of tectonic plates, where continents collide, where ocean floor dives beneath solid land in violent subduction, where the crust tears itself apart in fury. The Pacific Ring of Fire with its chain of deadly peaks. The Andes, where South America rides over the Nazca Plate. Iceland's volcanic fields, sitting astride the mid-Atlantic ridge where the Earth itself pulls apart. These locations make sense. The science is clear. Magma rises where plates meet. But Changbaishan? It sits in the middle of nowhere. 1,000 kilometers from the nearest plate boundary, rising from the stable heart of northeastern China, in a region that should be geologically dormant, silent, cold, dead. Yet this mountain produced an eruption so massive it ejected 100 cubic kilometers of material into the atmosphere. That's enough volcanic rock to bury the entire city of London under 200 meters of ash and pumice. Enough to blanket an area the size of Belgium. The ash from that single day in 946 has been found in ice cores from Greenland, in sediment layers across the Sea of Japan, in soil samples from northern Honshu. The mountain touched half a hemisphere. The question that has haunted volcanologists for decades is simple and deeply unsettling. Why is China's largest volcano where it shouldn't be? What force could birth such a monster in the geological equivalent of a quiet suburb? What power sleeps beneath this mountain so far from where volcanoes belong? And perhaps more importantly, more urgently, could it happen again? Today, the caldera of Changbaishan cradles Heaven Lake, Tianqi, one of the deepest crater lakes on Earth. Its waters are pristine, impossibly blue, breathtakingly beautiful. 213 meters deep in places. Cold, clear, tourists visit by the thousands each year, walking along the rim of this ancient wound, taking photographs, breathing the mountain air. Most are unaware they stand on the edge of a sleeping giant, but scientists know better. They watch, they measure. They remember what this mountain can do. Because beneath that serene surface something stirs. Minor earthquakes, small but persistent, rumble through the bedrock. Gases rise through the water, carbon dioxide, sulfur compounds, whispers from the deep. Satellite measurements detect subtle ground deformation, millimeters per year perhaps. But movement nonetheless. The mountain breathes. Instruments placed around the caldera record temperature fluctuations in the lake. Geochemists analyze the water, searching for changes in mineral content. Seismographs listen to the Earth's heartbeat below. And what they hear is not the silence of extinction. The mountain is not dead. It never was. It's simply waiting. To understand why Changbaishan defies explanation, we must first understand the rules it breaks. For most of human history, volcanoes were mysteries. Acts of divine anger. Doorways to the underworld. The forges of ancient gods hammering beneath the earth. But in the 20th century, we uncovered the truth. And it was, in its own way, just as extraordinary. The Earth's surface is not solid, not permanent. It's a puzzle of massive plates, drifting across a molten interior at speeds measured in centimeters per year. Continents ride these plates like passengers on vast stone rafts. And where these plates meet, where they collide or separate or slide past one another, that's where the Earth bleeds fire. This is plate tectonics. the grand theory that explains our restless planet. And according to this theory, volcanoes belong in specific places. Most great volcanoes sit above subduction zones. Here, an oceanic plate, cold, heavy, dense, dives beneath a continental plate. It descends into the Earth's mantle, where immense pressure and heat cause water trapped in the rock to be released. That water lowers the melting point of the surrounding mantle. Magma forms, rises, breaks through. The result? Volcanic arcs. Chains of fire. Japan's volcanic islands. The Cascades of North America, where Mount St. Helens and Mount Rainier brood. Indonesia's deadly ring, home to Krakatoa and Tambora. The Andes stretching like a backbone of fire down South America's western edge. These volcanoes make sense. The science is elegant. Beautiful, even. Then there are volcanoes at divergent boundaries, places where plates pull apart. Iceland sits atop the mid-Atlantic ridge, where the Eurasian and North American plates separate. Magma wells up from below to fill the gap, new crust is born. Volcanoes erupt with regularity, building the island year by year, century by century. Again, the pattern holds. The rules apply. And finally, there are hotspots. Plumes of superheated rock rising from deep within the mantle, perhaps from the boundary with the Earth's core itself. These thermal pillars remain relatively stationary while plates drift above them. Hawaii is the classic example. A conveyor belt of islands, each one marking where the Pacific plate passed over the hotspot millions of years ago. Yellowstone. The Galapagos. Reunion Island in the Indian Ocean. Hotspots explain volcanoes in strange locations. They're the exception that proves the rule. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. So when scientists first turned their attention to Changbaishan, they expected to find one of these explanations waiting. Perhaps an ancient subduction zone, long extinct but still capable of producing residual magma. Perhaps a hotspot, deep and powerful, feeding this isolated giant. What they found instead was nothing. No subduction zone within 1,000 kilometers. No hotspot signature in the mantle beneath. No divergent boundary. No plate edge of any kind. Changbaishan sits on the Eurasian plate, firmly inland, surrounded by stable continental crust that hasn't seen tectonic violence in hundreds of millions of years. The nearest active plate boundary is the Japan Trench, where the Pacific plate subducts beneath Japan. But that's on the other side of the Sea of Japan. Too far, the angles don't work. The chemistry doesn't match. This is what makes Changbaishan so unusual, so unsettling. It's an intraplate volcano, a giant rising from the middle of a tectonic plate far from any boundary. And while small intraplate volcanic fields exist scattered across the world, true giants like Changbaishan are vanishingly rare. The mountain shouldn't exist, yet it does. And in 946, it produced one of the largest eruptions in recorded history. For decades, this paradox haunted researchers. Expeditions were mounted. Rock samples collected from the slopes in the caldera rim. Seismic surveys conducted, sending sound waves deep into the earth to map what lay below. Geochemical analyses performed on the lava and ash, searching for clues about the magma's origin. Slowly, painstakingly, a picture began to emerge. And it revealed something extraordinary happening beneath northeastern China. Something that challenges our understanding of how the Earth works. Deep below Changbaishan, hundreds of kilometers down, the Pacific plate is doing something unexpected. As it subducts beneath Japan, diving into the mantle, it doesn't simply descend at a steep angle and disappear. Instead, it flattens, extends horizontally, reaches westward beneath the Asian continent like a tongue of cold, dense rock. And where this slab stagnates, where it releases water and volatile compounds into the mantle above, conditions change. The mantle melts. Magma forms, rises, finds a path to the surface, finds Changbaishan. But this explanation, elegant as it seems, raises more questions than it answers. Why here? Why this specific location and not elsewhere along the vast expanse where the Pacific slab extends? Why such violence? Why an eruption that rivals the greatest volcanic events in human memory? And why, after centuries of silence, is the mountain showing signs of unrest once more? Before the mountain exploded, it slept for centuries beneath the watch of empires. The year 946 belonged to a world we barely recognize. Europe was fragmented into feudal kingdoms. The Byzantine Empire still commanded the eastern Mediterranean. In China, the Tang dynasty had recently collapsed, giving way to a period historians call the Five Dynasties and Ten Kingdoms, a time of division, uncertainty, and change. And on the border between what would become China and Korea, Changbaishan stood tall. Rewrote. The mountain had erupted before, of course. Many times. Layers of ancient ash buried in the soil tell stories stretching back thousands of years, small eruptions, moderate ones. The mountain clearing its throat, so to speak, releasing pressure from the chambers below. But nothing in its recent history suggested what was coming. Nothing prepared the world for what the mountain was about to do. We know frustratingly little about the human communities living near Changbaishan in those final years before the eruption. The historical record is sparse, fragmentary. Written accounts from the period focus on dynasties and wars, on the rise and fall of emperors, on the great sweep of political history. The lives of farmers and herders, of small villages nestled in mountain valleys, rarely made it into the chronicles. But we can imagine them. We must imagine them. Families who had lived in the shadow of the mountain for generations. Communities who drew water from streams fed by the mountain slopes. People who looked up at the peak each morning and evening, watching clouds gather around its summit, watching snow blanket its upper reaches in winter. Perhaps they told stories about the mountain. Legends of gods and spirits dwelling within. Tales of smoke seen rising from the crater in their grandparents' time or their great-grandparents'. Warnings passed down through generations about respecting the mountain's power. Perhaps some elders still remembered smaller eruptions. Steam venting from the summit. The smell of sulfur carried on the wind. Earthquakes that rattled homes and sent livestock into panic. Or perhaps those memories had faded. Perhaps the mountain had been quiet for so long that people stopped worrying. Stopped watching, stopped believing it could awaken. This is often how it happens, you see. Volcanoes sleep for centuries and human memory is short. Villages grow, towns expand. People build closer and closer to danger, forgetting what the earth can do. But the mountain did not forget. Deep below, processes beyond human perception were underway. Magma was accumulating, rising through fractures in the crust, pooling in chambers kilometers beneath the surface. The pressure was building, slowly, inexorably, year after year. Decade after decade, until finally the rock could hold no more. We don't know if there were warning signs in the days or weeks before the eruption. Modern volcanic monitoring didn't exist, of course. No seismographs to detect earthquakes. No gas sensors to measure sulfur dioxide emissions. No satellite imagery to track ground deformation. But nature always provides warnings if one knows how to read them. Perhaps there were earthquakes. Small tremors at first, then growing stronger and more frequent. The kind that wake you in the night, that send dishes clattering and animals fleeing. Perhaps the streams and rivers changed. Water turning cloudy or acidic. Fish dying. Hot springs growing hotter, their water taking on unusual colors or smells. Perhaps the mountain itself changed. Steam or gas venting from the crater. The snow on the upper slopes melting out of season. Trees dying in patches where volcanic gases seeped from the ground. These are the signs modern volcanologists look for. The signals that a volcano is restless, awakening. But in 946, who was watching? Who knew how to interpret these omens? And even if someone noticed, even if concern spread through the villages, what could they do? Where could they go? The mountain had been part of the landscape forever, unchanging, eternal, until it wasn't. What happened next unfolded over hours, perhaps days. The exact timeline is lost to history. But volcanology gives us a framework. A script that violent eruptions tend to follow, first an opening phase. The pressure finally exceeds the strength of the rock. The summit fractures. An initial explosion clears the vent. A blast of steam, ash, and rock fragments. Not the main event, just the overture. Then, as the pressure drops and magma rises more freely, the eruption intensifies. A sustained column of ash and pumice roars skyward, 4, 5, 6 kilometers high, then 10, 20, 30. The column is a mixture of rock, glass shards, and superheated gas, all suspended in a churning, turbulent jet. It rises because it's hot, less dense than the surrounding air, powered by the expanding gases dissolved in the magma. At this stage, people many kilometers away would see the column, a towering pillar of darkness rising from the mountain, growing, spreading at the top into a shape that ancient observers compared to a Mediterranean pine tree, what we now call a Plinian column, after Pliny the Elder's description of Vesuvius. The sound would be constant, a roar like continuous thunder, or like standing next to a waterfall the size of a mountain. A sound felt in the chest as much as heard, and then the wind would shift, and the ash would begin to fall. At first, fine particles, a dusting, easily dismissed. But hour after hour, the ash continues, thickening, accumulating, covering everything in gray. Roofs collapse under the weight. Crops are buried. Livestock suffocate. Breathing becomes difficult, painful. This is how volcanic ash kills, not dramatically, not in a single moment, but through suffocation, through burial, through the slow, grinding destruction of everything a community needs to survive. And still the mountain roars, still the column rises. For Changbaishan, this phase may have lasted hours. A day, perhaps longer. The total volume ejected, 100 cubic kilometers. Dense rock equivalent. Imagine a cube 10 kilometers on each side, lifted from deep within the earth and scattered across the landscape. This puts the Millennium Eruption firmly in the VA6 category, Volcanic Explosivity Index 6, one step below the catastrophic VA7 events like Tambora, but still large enough to affect climate, to alter history. And then came the moment when the eruption changed, when it stopped being a spectacle and became a catastrophe. The eruption column, that massive tower of ash and gas rising 30 kilometers into the stratosphere, had been sustained by the sheer force of gases expanding from the magma. Pressure from below kept it aloft, kept it climbing. But no eruption can maintain that intensity forever. Eventually, the gas content drops. The pressure weakens. The column can no longer support its own weight. And when that happens, when that critical threshold is crossed, the column doesn't simply stop. It doesn't gently dissipate. It collapses. Billions of tons of superheated ash, pumice, and rock fragments fall back to Earth, but they don't fall slowly. They fall as an avalanche. A pyroclastic density current. A ground-hugging tsunami of stone and gas moving at speeds that can exceed 200 kilometers per hour. Temperature, anywhere from 400 to 700 degrees Celsius. Hot enough to incinerate anything organic instantly. Hot enough to melt metal. This is what transformed the Millennium Eruption from dangerous to apocalyptic. Pyroclastic flows move like fluids, but they're not liquid. They're a mixture of solid particles suspended in gas, flowing downhill with terrifying speed, following valleys, wrapping around obstacles, filling every depression in the landscape. They move faster than any human can run, faster than most animals can flee. And they give no warning beyond the roar of their approach, a sound witnesses have compared to a freight train or a jet engine or the end of the world. At Changbaishan, when the column collapsed, these flows raced down every slope, north, south, east, west, channeled by the mountain's topography, accelerated by gravity unstoppable. Forests that had stood for centuries were obliterated in seconds. Trees didn't burn, there wasn't time. They were simply erased, snapped, stripped of branches, carbonized where they stood. Any villages in the path vanished. Completely, the flows don't leave ruins. They don't leave survivors. They leave only a blanket of pumice and ash, meters thick, bearing everything beneath. We don't know how many people died. The historical records are silent. Perhaps the population was sparse enough that most were beyond the reach of the flows. Perhaps entire communities were lost, their names forgotten, their stories erased along with everything they built. What we know is this: pyroclastic flows from Changbaishan traveled at least 20 kilometers from the summit. Possibly farther. The deposits remain visible today. More than 1,000 years later, thick layers of gray and white pumice exposed in road cuts and stream banks. But the flows were only one part of the destruction. As the eruption continued, as more and more magma was ejected, the mountain was hollowing itself out. The chamber below the summit, the reservoir that had fed the eruption, was draining, emptying, and without support, without the pressure from below that had held it up, the summit did what physics demanded. It collapsed inward. Not slowly, catastrophically. The entire top of the mountain fell into the void below. Thousands of feet of rock simply disappeared into the earth. The sound must have been beyond description. The ground would have shaken for hundreds of kilometers in every direction. What remained was a caldera. A vast circular depression where a mountain peak had once stood, 5 kilometers across, nearly a kilometer deep in places. This is how calderas form, not through erosion. Not gradually, but in moments of supreme violence when a volcano consumes itself. Krakatoa did this in 1883, Tambora in 1815. Santorini, 3,000 years ago in an eruption that may have helped end the Minoan civilization. And Changbaishan in 946. When the eruption finally ended, when the magma stopped rising, when the flows ceased, when the ash stopped falling, the landscape had been transformed beyond recognition. Where villages had stood, there was only gray wasteland. Where forests had covered the slopes, there were fields of pumice. Where a mountain peak had touched the sky, there was emptiness. The caldera smoked, vented steam and gases. The walls were unstable, subject to landslides. In some places, the ground was still hot enough to ignite anything organic. In others, fine ash created a choking dust with every breath of wind. For years afterward, perhaps decades, the region would have been nearly uninhabitable. Ash contaminated water sources. Crops failed. The few survivors, if any remained nearby, would have fled. And in the caldera itself, water began to accumulate, rainwater, snowmelt, groundwater seeping up through fractured rock. Year by year, century by century, the caldera filled. Today we call it Heaven Lake Tianchi, one of the deepest and most beautiful crater lakes on Earth. But beneath that beauty lies the memory of violence. The ash from the Millennium Eruption traveled extraordinary distances. Prevailing winds carried it eastward across the Sea of Japan. Significant deposits fell on the northern Japanese island of Hokkaido, where they remain visible today as a distinct layer in the soil, a marker horizon that allows archaeologists and geologists to date other findings above and below it. Traces have been found as far south as Honshu, as far east as the Pacific Ocean floor. The finest particles, microscopic glass shards, reached the stratosphere and circled the globe. Did the eruption affect climate? Almost certainly. These 6 eruptions typically cool global temperatures by injecting sulfur dioxide into the stratosphere, where it forms reflective aerosol particles that scatter sunlight. The effect lasts 1 to 3 years typically. Whether the Millennium Eruption contributed to crop failures or unusual weather in distant lands, we may never know. Historical records from Europe and the Middle East in the mid-10th century don't mention anything extraordinary. But Asia was fragmented, communication was limited, and a year of cold weather or poor harvests might have been attributed to bad fortune or divine displeasure, not to a volcano thousands of kilometers away. In the centuries following the eruption, the mountain slept. The caldera cooled. The lake deepened. Life returned slowly to the slopes. First lichens and mosses, then shrubs, then trees. Animals returned. Birds nested in the new forest. And eventually people returned too, drawn by the mountain's beauty, by the resources it offered. Perhaps forgetting or never knowing what had happened here, the mountain became sacred again. Heaven Mountain, a place of pilgrimage and legend. But beneath the surface, the processes that created the eruption never stopped. The magma source remains. The Pacific Plate continues its slow dive into the mantle. Water continues to be released. Melting continues. Changbaishan is not extinct. Volcanologists classify it as active. Dormant, perhaps, but not dead. And in recent decades, the mountain has begun to stir once more. For most of the 20th century, Changbaishan remained a geological curiosity, a puzzle without a solution. Scientists knew it existed. They knew it had erupted catastrophically. They could see the caldera, measure its dimensions, analyze the ash deposits scattered across northeastern Asia. But they couldn't explain it. The mountain violated every rule. It sat where no volcano should exist. And that inconsistency gnawed at researchers. Because science demands explanations. Patterns, laws that apply everywhere, not just in convenient locations. If Changbaishan could exist, if a giant volcano could rise from the stable interior of a continent, far from any plate boundary, then what else didn't we understand about our planet? The answer would require decades of research. Seismic studies, geochemical analysis, computer modeling of the mantle beneath Asia, and slowly, piece by piece, the picture emerged. What they discovered changed our understanding of how volcanoes work. The key lies deep beneath northeastern China, hundreds of kilometers below the surface, in the realm of the upper mantle where rock behaves like a viscous fluid over geological time. Here, something extraordinary is happening. Something invisible from the surface, but revealed by seismic tomography, a technique that uses earthquake waves to create three-dimensional images of the Earth's interior, much like a medical CT scan images the human body. When seismic waves pass through cold, dense rock, they travel faster. When they pass through hot, less dense rock, they slow down. By measuring these variations from earthquakes recorded at hundreds of stations across Asia, scientists can map temperature and density structures deep underground. And what they found beneath Changbaishan was startling, a massive anomaly. A region where seismic waves slow dramatically. This indicates hot rock, partially molten rock. A thermal plume rising from depth, carrying heat and material toward the surface. But where does this heat come from? What drives it upward? The answer lies not directly beneath Changbaishan, but hundreds of kilometers to the east. Beneath Japan, the Pacific Plate is doing what it has done for millions of years, subducting beneath the Eurasian Plate, diving into the mantle at the Japan Trench. This is normal, expected. It's why Japan has so many volcanoes. But the Pacific Plate doesn't simply descend at a steep angle and disappear into the deep mantle. Instead, at a depth of around 400 to 600 kilometers, something changes. The slab encounters resistance, perhaps a boundary in the mantle where density changes. Perhaps the viscosity increases. Whatever the cause, the slab's descent slows, flattens, instead of continuing straight down, it extends horizontally beneath the Asian continent. Westward, a tongue of cold, dense oceanic crust pushing beneath northeastern China. Scientists call this a stagnant slab. And it's the key to understanding Changbaishan. As the Pacific slab subducts, it carries water with it. Not liquid water. At these pressures and temperatures, water exists chemically bound within minerals. Hydrated minerals formed when the oceanic crust was at the surface, when seawater percolated through cracks and fractures. But as the slab descends, pressure and temperature increase. Eventually, these minerals break down. The water is released. And water changes everything. When water is introduced into hot mantle rock, it lowers the melting point. Rock that would otherwise remain solid begins to melt, partially at first, but enough to create magma. Enough to initiate a process that feeds on itself. The magma is less dense than the surrounding rock. It's buoyant. It begins to rise. Slowly at first, percolating upward through tiny channels and fractures. But as it rises, it melts more rock. Grows in volume. Eventually forms larger bodies, diapirs, that ascend like bubbles through honey. This is how subduction zone volcanoes work. It's the mechanism behind the ring of fire. The process is well understood. But at Changbaishan, there's a critical difference. The subducting slab isn't directly beneath the volcano. It's hundreds of kilometers away. The water released from the stagnant slab has to travel laterally through the mantle, carried by convection currents before it reaches the region beneath Changbaishan. And somewhere along that journey, the chemistry changes, the magma evolves, becomes richer in certain elements, develops characteristics that distinguish it from typical subduction zone volcanoes. Geochemists have analyzed the composition of Changbaishan's lavas and ash. They've measured isotope ratios, the relative abundance of different atomic forms of elements like strontium, neodymium, and lead. These ratios act like fingerprints, revealing the source of the magma. What they found is a mixture. A hybrid. The magma carries signatures from the subducted Pacific Plate, elements and isotopes typical of oceanic crust that has been altered by seawater. But it also carries signatures from the continental crust and the mantle wedge beneath Asia. This tells a story of complexity, of magma that has interacted with multiple sources as it rose, that has assimilated continental material, that has mixed and evolved and changed. It's not a simple system, not a straightforward process. And perhaps that's why Changbaishan is so explosive. Why the Millennium Eruption was so violent. The magma is rich in dissolved gases, water vapor, carbon dioxide, sulfur compounds. These gases remain dissolved under high pressure deep underground. But as the magma rises, as pressure decreases, the gases begin to exsolve, to form bubbles. It's exactly like opening a bottle of champagne. At high pressure, carbon dioxide stays dissolved. Open the bottle, pressure drops, and the gas comes out of solution explosively. In a volcano, this process drives eruptions. The expanding gases fragment the magma into tiny particles, ash and pumice. They propel the eruption column skyward. They power pyroclastic flows. And if the magma is particularly gas-rich, if it rises quickly without losing those gases gradually, the eruption can be extraordinarily violent. This is what happened in 946. This is why the Millennium Eruption was so powerful. But there's still a deeper question, a more fundamental mystery. Why Changbaishan specifically? Why this location and not elsewhere along the vast expanse where the stagnant Pacific slab extends beneath Asia? This is where geology becomes more speculative, more uncertain. One possibility involves ancient structures in the continental crust. Zones of weakness, old faults, rifts, or sutures where continents collided hundreds of millions of years ago. These structures can act as pathways, allowing magma to rise more easily. Another possibility involves the exact geometry of the stagnant slab. Perhaps there's a tear or gap in the slab beneath Changbaishan, a window where hot mantle material can well up from below, creating additional melting. Or perhaps it's simply a matter of chance and time. The magma finds the path of least resistance. It accumulates where conditions allow. And over millions of years, a volcanic system develops. We may never know for certain. The Earth keeps some secrets. What we do know is this: Changbaishan is not alone. Across northeastern China and into North Korea, there are other volcanic fields. Smaller, less dramatic, but also intraplate volcanoes, also sitting far from plate boundaries, also fed by processes linked to the stagnant Pacific slab. This is a volcanic province, a region where the impossible happens, where the Earth, yes interior, finds ways to express itself despite being far from the usual zones of activity. And that makes it unpredictable, dangerous, fascinating. After more than 1,000 years of silence, Changbaishan began to stir. It happened gradually, subtly, the kind of changes only instruments could detect at first. The kind of signs that, in an earlier age, would have gone completely unnoticed. But we live in an era of volcanic monitoring. An age where satellites watch from space, where seismometers listen to the Earth's tremors, where gas sensors sniff the air for chemical warnings. And, in the early years of the 21st century, those instruments began registering something unusual. The mountain was waking up. It started with earthquakes, small ones. Magnitude 2, magnitude 3. The kind most people wouldn't feel unless they were standing directly above the epicenter. But to volcanologists, earthquake swarms beneath a volcano are never trivial. They're signals. Messages from deep underground telling us that something is moving, that pressure is changing, that the system is becoming active. In 2002 and 2003, Changbaishan experienced its most significant seismic unrest in recorded history. Thousands of small earthquakes clustered beneath the caldera. Some shallow, just a few kilometers deep. Others deeper, extending down to 10 or 15 kilometers. The pattern was telling. It suggested magma movement, or the migration of volcanic fluids, superheated water and gases, through fractures in the rock. Scientists from China, North Korea, and international institutions mobilized. Monitoring stations were established. GPS receivers were installed to measure ground deformation. Gas sampling began in earnest. What they found was concerning. The ground around the caldera was rising, not dramatically. Not in a way you could see with the naked eye. But satellite radar interferometry, a technique that compares images taken months or years apart, revealed the change clearly. Several centimeters of uplift, spread across an area several kilometers wide, centered on the caldera. This is what happens when magma or volcanic fluids accumulate at depth. The pressure from below pushes upward. The surface responds by bulging, slowly, inexorably. It's a pattern seen at volcanoes worldwide before eruptions. Mount St. Helens did this in the months before its catastrophic 1980 eruption. The bulge on its north flank grew by more than 100 meters before the mountain finally exploded. At Changbaishan, the deformation was far more subtle. But it was real and it was accelerating. Then there were the gases. Volcanic gases provide some of the most important clues about what's happening deep underground. When magma rises, when it approaches the surface, gases dissolved in the melt begin to escape. They percolate upward through cracks and fractures. They emerge at the surface through fumaroles, hot springs, and the soil itself, carbon dioxide, sulfur dioxide, hydrogen sulfide, helium with isotope ratios that betray a deep mantle source. Around Changbaishan, gas emissions increased. Springs that had been cool began to warm. The concentration of volcanic gases in the caldera atmosphere rose measurably. And in Heaven Lake itself, that pristine crater lake filling the caldera, scientists detected temperature anomalies. Patches where the water was warmer than it should be. Areas where gases bubbled to the surface. The lake, it seemed, was being heated from below. By 2005, concern had escalated to the point that Chinese authorities established a permanent volcanic observatory near the mountain. Seismometers were deployed in a network around the caldera. Continuous GPS stations monitored ground movement in real time. Gas sensors sampled the air constantly. The mountain was placed under surveillance, 24 hours a day. Every tremor recorded, every millimeter of movement noted. And what the data showed was a volcano that had not returned to sleep. The seismicity continued. The deformation persisted. The gases kept coming. Changbaishan was not on the verge of imminent eruption. There was no indication that magma had reached the shallow depths, a kilometer or two below the surface, where an eruption becomes likely in the near term. But the system was clearly active, restless, and volcanoes on human timescales can be maddeningly unpredictable. They can show signs of unrest for years, even decades, without erupting. Or they can transition from quiet to explosive in a matter of weeks. The challenge facing scientists was, and remains, determining what comes next. Is this unrest simply the volcano's normal breathing? The natural circulation of fluids in a geothermal system that has been active for millions of years? Or is it the prelude to something more? The early warning of an eruption that could dwarf anything in modern memory? The honest answer is, we don't know. Volcanology is not a predictive science in the way we might wish. We can monitor. We can observe patterns. We can say when a volcano is becoming more likely to erupt based on historical precedent. But we cannot tell you the day, the hour, or even with certainty whether an eruption will occur at all. What we can say is this: the signs at Changbaishan are consistent with magma or volcanic fluids moving beneath the surface. The earthquakes, the deformation, the gases, these are not random. They're connected. They tell a coherent story of a volcanic system that is active. And that makes Changbaishan a volcano to watch very carefully. Because the stakes are extraordinarily high. Today, more than 2 million people live within 100 kilometers of Changbaishan. Cities have grown where once there were only villages. Infrastructure has been built. Roads, railways, bridges. The region is no longer remote or isolated. An eruption on the scale of 946 would be catastrophic. Pyroclastic flows could devastate areas dozens of kilometers from the summit. Ashfall would disrupt agriculture, contaminate water supplies, and shut down air travel across northeastern Asia. And unlike in 946, we would have advance warning. The monitoring network would detect accelerating seismicity, rapid deformation, sharp increases in gas emissions. We would know days, perhaps weeks in advance that an eruption was imminent. But knowing is not the same as being prepared. Evacuating millions of people is a logistical nightmare. Where do they go? How long must they stay away? How do you convince populations to leave their homes based on probabilities and scientific uncertainties? These are not just scientific questions. They're social, political, and deeply human questions. And Changbaishan forces us to confront them. After the intense unrest of 2002 to 2005, the volcano quieted somewhat. Seismicity decreased. The rate of deformation slowed. Gas emissions stabilized. Some scientists interpreted this as a return to background levels, a false alarm. The volcano had vented pressure, adjusted its internal plumbing, and settled back into dormancy. Others were less convinced. They pointed out that volcanoes often show episodic unrest, periods of activity followed by quiet periods. And each episode can bring magma closer to the surface, can prime the system for an eventual eruption. The debate continues. Monitoring continues. The instruments keep watching, keep listening. Because volcanoes operate on geological time, and to the Earth, a few decades is nothing. Less than a heartbeat, the mountain will erupt again. That much is certain. Whether it happens in our lifetimes, our children's lifetimes, or centuries from now is the question we cannot answer. But the mountain is patient. And it remembers what it can do. There's a particular challenge that comes with monitoring a volcano like Changbaishan. It's not the technology. Modern instruments are remarkable. Sensitive enough to detect ground movement measured in millimeters. Precise enough to identify earthquake hypocenters to within a few hundred meters. Sophisticated enough to analyze gas compositions in real time. The challenge is interpretation, context, knowing what the data means, because every volcano is unique. Each has its own personality, its own patterns of behavior. And for a volcano that has been quiet for more than 1,000 years, we have no modern baseline. No living memory of what the precursors to an eruption actually look like. The 2002 to 2005 unrest at Changbaishan raised alarm precisely because we couldn't compare it to anything. Was this normal background activity? Or was it the beginning of a reawakening that would culminate in eruption? To answer that question, scientists turned to other volcanoes, to the historical record, to comparisons that might offer insight. And what they found was both reassuring and deeply unsettling. Consider Mount Paektu in the Philippines. Before 1991, it had been dormant for more than 500 years, considered extinct by many. Its slopes were heavily forested, populated, cultivated. Then in March 1991, villagers reported steam explosions near the summit. Small earthquakes began. Within weeks, the seismicity intensified dramatically. Thousands of earthquakes per day, ground cracking, sulfur dioxide emissions skyrocketing. Scientists recognized the warning signs. An evacuation was ordered. And on June 15, 1991, Pinatubo erupted with a violence that shocked the world. A V6 eruption, the same magnitude as Changbaishan's Millennium Eruption. Pyroclastic flows devastated the landscape. Ash buried entire towns. Nearly 1,000 people died, most from roofs collapsing under the weight of ash mixed with rain from a passing typhoon. But tens of thousands were saved. Because the monitoring worked. Because scientists interpreted the signs correctly. Because authorities acted on uncertain information and evacuated populations before the eruption. Pinatubo became a success story in volcanic crisis management. Proof that monitoring saves lives. But not all stories end so well. Mount Paektu in Japan erupted without significant warning in September 2014. A small eruption by volcanic standards. A brief phreatic explosion caused by steam pressure rather than rising magma. Day 1 or 2 at most. But it occurred on a clear Saturday afternoon. The mountain was crowded with hikers enjoying the autumn weather. 63 people died, caught near the summit when the eruption began. Japan's deadliest volcanic disaster in nearly a century. Seismicity had increased slightly in the weeks before. Gas emissions had changed. But the signs were subtle. Ambiguous, not clearly pointing to imminent eruption. And so the mountain remained open, and people died. These cases illustrate the fundamental tension in volcano monitoring. Act too cautiously and you cry wolf. Evacuate populations unnecessarily. Cause economic disruption, erode public trust, create complacency for the next warning. Act too conservatively and people die. It's an impossible balance. A judgment call that scientists and authorities must make with incomplete information, under enormous pressure, knowing that lives hang on their decisions. At Changbaishan, this tension is magnified by the sheer scale of potential impact, the population at risk, the economic importance of the region, and the political complexity of a volcano that sits on the border between China and North Korea. Any eruption crisis would require coordination between governments that don't always communicate easily. Evacuation plans that span international boundaries. Resources deployed across contested or sensitive areas. These are not trivial considerations, and they add layers of difficulty to an already challenging situation. So what have scientists learned from studying Changbaishan over the past 2 decades? First, that the volcano has a robust geothermal system. Hot fluids circulate beneath the caldera, driven by residual heat from the magma chamber and possibly by continued small inputs of fresh magma from depth. This system causes much of the observable activity, the seismicity, the gas emissions, the thermal anomalies in Heaven Lake, Most of this activity is not directly related to an impending eruption. It's the volcano's normal state, its background noise. The trick is distinguishing background from signal, routine from critical. Second, that the magma system beneath Changbaishan is complex and likely still active. Seismic tomography shows low-velocity zones, regions of hot, possibly partially molten rock extending from the upper mantle to depths of just 10 or 15 kilometers below the surface. This is uncomfortably shallow. Magma at these depths can reach the surface in a matter of days or weeks if a pathway opens. But the mere presence of shallow magma doesn't mean eruption is imminent. Many volcanoes maintain shallow magma bodies for decades or centuries without erupting. The magma can cool, crystallize, solidify in place. Eruption requires more than just magma. It requires the right conditions, sufficient gas content, high enough pressure, a trigger to initiate the ascent. Third, that precursors to a major eruption at Changbaishan, if one were to occur, would likely be detectable. Not subtle. Not easily missed. The 1991 Pinatubo example is instructive. In the weeks before eruption, seismicity reached extraordinary levels. 10,000 earthquakes recorded in a single day, continuous volcanic tremor, explosive steam venting, massive sulfur dioxide emissions. These are unmistakable signs. A volcano screaming that it's about to erupt. At Changbaishan, if magma begins rising toward the surface in earnest, the monitoring network will detect it. The seismicity will intensify. The deformation will accelerate. The gas chemistry will change dramatically. Scientists will have warning. Time to assess. Time to alert authorities. The question is how much time, and whether it will be enough. Because the other lesson from studying eruptions worldwide is that the final transition from unrest to eruption can be abrupt. Magma that has been slowly ascending can suddenly accelerate. A fracture opens. Pressure drops. Gases exsolve explosively. And what was a gradual process becomes violent in hours. This is what happened at Mount St. Helens in 1980. Months of earthquakes and deformation. A growing bulge on the mountain's flank. Then on the morning of May 18th, a magnitude 5 earthquake triggered a massive landslide. The landslide removed the bulge, suddenly releasing the pressure that had been confining the magma chamber. The result was instantaneous, lateral blast. Pyroclastic flows. An eruption that transformed the landscape in minutes. At Changbaishan, a similar trigger could be an earthquake, or the intersection of rising magma with groundwater, causing a phreatic explosion that opens the vent, or simply the accumulated pressure exceeding the strength of the overlying rock. We cannot predict triggers, we can only watch and prepare. And so the monitoring continues, year after year. The instruments record data. Scientists analyze patterns. Models are refined. Emergency response plans have been developed for communities around the volcano. Evacuation routes identified. Shelters designated. Communication protocols established. Hazard maps show the areas at greatest risk. Zones where pyroclastic flows could reach. Regions likely to be buried under thick ash. Areas where lahars, volcanic mud flows, could sweep down valleys during heavy rain. These maps are based on the 946 eruption and on computer models of potential future eruptions. They're not predictions. They're scenarios, possibilities, but they're the best tools we have for planning, for preparedness. And they make one thing clear: when Changbaishan erupts again, the impact will be felt far beyond the immediate vicinity of the volcano. Ash could affect air travel across northeastern Asia. Agricultural disruption could impact food supplies. Economic losses could reach into the billions. This is the reality of living with volcanoes in the modern interconnected world. The risks are not just local, they're regional, sometimes global. For all the science, all the monitoring, all the sophisticated instruments watching Changbaishan, there remains something deeply human about our relationship with this mountain. People have lived in its shadow for thousands of years. Long before the Millennium Eruption. Long before written history. Archaeological evidence suggests human presence in the region stretching back to the Stone Age. They hunted in the forests that covered the slopes. They fished the rivers that flowed from the mountain springs. They built settlements in the valleys, raised families, buried their dead. And they looked up at the mountain with reverence, with awe, perhaps with fear. Because humans have always recognized power when we see it. We may not have understood plate tectonics or magma chambers or volcanic gases, but we understood that mountains like Changbaishan were different. Sacred, dangerous, the mountain had many names over the millennia. In Korean, Paektu, meaning white head, for the snow that crowned its summit. In Chinese, Changbaishan, eternally white mountain. In Manchu tradition, it was Gulman Zangbian Alan, the sacred mountain. Legends accumulated around the peak like snow. Stories passed from generation to generation. In Korean mythology, Changbaishan is the birthplace of Donggon, the legendary founder of the First Korean Kingdom, Gujoshin, more than 4,000 years ago. The mountain appears in foundation myths, in tales of gods descending to earth, and stories that connect the Korean people to the land itself. For the Manchu people, the mountain was the ancestral home, the place where heaven touched earth, where spirits dwelled. The Qing dynasty, which ruled China from 1644 to 1912, considered Changbaishan sacred precisely because of these Manchu connections. Access to the mountain was restricted, carefully controlled. The mountain was not just geography. It was identity, heritage, a physical manifestation of cultural memory. And perhaps that's why, even after the catastrophic eruption of 946, people returned, why communities rebuilt, why the mountain continued to hold meaning beyond the danger it represented. Because humans are remarkably persistent, remarkably adaptable, and remarkably willing to live alongside risk when the alternative means abandoning something precious. Today, Changbaishan is a different kind of sacred space. A nature reserve, a tourist destination, a place of beauty rather than explicit worship. Heaven Lake draws hundreds of thousands of visitors annually. They come to see the impossibly blue water filling the caldera, to walk the rim trails, to photograph the stark volcanic landscape, to stand where the mountain once stood before it consumed itself. Most visitors know nothing of the geology, nothing of the 946 eruption or the volcanic processes still active beneath their feet. They see beauty, tranquility, a pristine alpine environment, and in a sense, they're not wrong. The mountain is beautiful. The lake is tranquil. The danger, if it exists, is potential rather than immediate. But for those who understand what they're looking at, the landscape tells a different story. The caldera walls, steep, unstable, scarred by erosion, speak of violence. The pumice deposits exposed in road cuts speak of flows that obliterated everything in their path. The very existence of the lake speaks of a summit that collapsed into emptiness. This is the paradox of volcanic landscapes. They're simultaneously beautiful and terrifying. Created by destruction. Shaped by forces that would kill us instantly if we were present when they acted. And yet we're drawn to them. We build on them, we make them part of our identity. The communities surrounding Changbaishan today are small by Chinese standards but significant nonetheless. Towns of tens of thousands. Cities of hundreds of thousands within the broader region. They depend on the mountain economically. Tourism provides jobs. The forests provide timber. The volcanic soils, rich in minerals, support agriculture. Geothermal energy heats homes and greenhouses. The mountain gives. And the mountain takes away. This has always been the bargain with volcanoes. Fertility in exchange for risk. Prosperity in exchange for vigilance. In some places, Iceland, Japan, Indonesia, this bargain is explicit. Part of the cultural understanding. People know they live on active volcanoes. They prepare. They teach their children what to do if the mountain wakes. In northeastern China, the memory has faded. The last major eruption was more than a millennium ago. Beyond living memory. Beyond historical memory for most people. And so there's a disconnect. The scientists monitoring the volcano understand the risk intellectually, quantitatively. But for the general population, Changbaishan is simply part of the landscape. Familiar, safe. This is dangerous. Because when a volcano that has been quiet for centuries finally erupts, people are unprepared. Psychologically. Practically. They don't believe it can happen. Even when scientists warn them. Even when evacuation orders are issued. This phenomenon, normalcy bias, has killed thousands throughout history. People staying in their homes during Vesuvius because they couldn't imagine their city being destroyed. People remaining in Pompeii until the pyroclastic surge arrived. Modern education helps. Drills help. Clear communication helps. But ultimately, preparedness requires accepting that the familiar can become deadly. That the mountain you've looked at every day of your life can transform into something else entirely. There's also a political dimension that cannot be ignored. Changbaishan sits on the border between China and North Korea. The summit itself, the caldera, straddles the boundary. Heaven Lake is divided between the two nations. This creates unique challenges for monitoring and emergency response. Scientific data must be shared across political boundaries. Evacuation plans must account for border dynamics. Resources must be coordinated between governments with complex relations. During the 2002 to 2005 unrest, this became apparent. Chinese scientists worked with international collaborators. North Korean scientists worked more independently, with less transparency. Information flowed unevenly. In a volcanic crisis, this could be catastrophic. An eruption doesn't respect borders. Pyroclastic flows don't stop at political boundaries. Ash falls on both sides of a line on a map. Effective response requires cooperation, communication, shared data, and shared decision-making. Whether that will happen in practice remains an open question. But perhaps the most profound human connection to Changbaishan is simpler, more fundamental. It's the recognition that we live on a dynamic planet. That the ground beneath our feet is not permanent, not stable. That forces beyond our control and vastly beyond our power shape the world we inhabit. Standing at the edge of Heaven Lake, looking down into water that fills a void created by unimaginable violence, you feel it. The scale. The indifference of geological processes to human concerns. The mountain doesn't care whether we study it or worship it or ignore it. It operates according to physics, chemistry, thermodynamics, laws that predate humanity and will outlast us. And yet we persist, we build, we study. We try to understand, we try to predict, because that's what humans do. We seek knowledge. We seek control, or at least the illusion of it. We refuse to accept that some things are simply beyond us. And sometimes, as with Pinatubo, our efforts succeed. We save lives, we turn knowledge into action, into survival. Other times, as with Ontake, we fail. The warning signs are too subtle. The eruption too sudden. And we're reminded of our limitations. Changbaishan will erupt again, that is certain. The only questions are when and how large and whether we'll be ready. The monitoring continues, the research continues. Plans are refined, models improved. And people continue to live in the shadow of the mountain. Continue to draw water from streams fed by its springs. Continue to look up at the peak and see beauty, history, identity. This is not foolishness. Or if it is, it's the same foolishness that has driven humans to inhabit river deltas that flood, coastlines that face hurricanes, fault zones that produce earthquakes. We live with risk because the alternative is to live nowhere. Because every place has dangers. And some places, despite the dangers, are worth the risk. Changbaishan is one of those places. Sacred, beautiful, deadly, human. There's a question that haunts every conversation about Changbaishan, every scientific paper, every risk assessment, every emergency planning meeting. When will it erupt again? It's the question everyone asks. Scientists, authorities, residents, tourists standing at the caldera rim, looking down into Heaven Lake, suddenly aware they're standing on an active volcano. And the answer, frustrating as it may be, is that we simply don't know. Not next year, not next decade. Perhaps not for centuries or perhaps tomorrow. Volcanoes do not operate on human schedules. They operate on geological time. And our window of observation, a few decades of modern monitoring, is a blink of an eye in the mountain's history. What we can say is this: the mountain will erupt again. The magma source remains active. The processes that created the Millennium Eruption haven't stopped. They continue deep beneath the surface, driven by the slow descent of the Pacific Plate, by the release of water into the mantle, by the generation of magma that will eventually find its way upward. The only question is when. Statistical analysis of Changbaishan's eruptive history suggests an average interval of several centuries between major eruptions. But averages are deceptive. Volcanoes don't erupt on regular schedules like clockwork. They erupt when conditions are right. When pressure exceeds the strength of the confining rock. When a trigger, an earthquake, a destabilization, a critical threshold initiates the process. Some volcanoes erupt frequently. Iceland's Hekla erupted 5 times in the 20th century. Mount Etna in Sicily erupts almost continuously, producing small lava flows and strombolian activity year after year. Others sleep for millennia between eruptions. Mount Mazama in Oregon, now Crater Lake, erupted catastrophically 7,700 years ago and has unerupted since. Yellowstone's last major eruption was 640,000 years ago. Changbaishan, with its 1,000-year interval since the last major eruption, falls somewhere in the middle. Not hyperactive, not dormant for geological epochs, simply waiting, and that waiting can end at any time. This uncertainty creates profound challenges for risk management. How do you prepare for something that might not happen in your lifetime? How do you maintain vigilance over decades, generations when the mountain remains quiet? How do you justify the expense of monitoring networks, of research programs, of emergency preparedness when the threat is abstract? Potential rather than immediate? These are not just technical questions. They're questions about human nature, about how we perceive risk, about the tension between present needs and future possibilities. History suggests we're not particularly good at this. We prepare for the disasters we've experienced, not the ones we haven't. We respond to immediate threats, not distant possibilities. We remember for a while, then forget. After major eruptions, monitoring improves. Research intensifies. Plans are made. Then decades pass. Budgets are cut. Attention shifts elsewhere. Instruments fall into disrepair. And when the volcano finally awakens, we're caught unprepared all over again. But there are reasons for hope. Reasons to believe that this time might be different. First, the scientific community has achieved something remarkable over the past few decades: global cooperation. Volcanic observatories share data. Researchers collaborate across borders. Lessons learned at one volcano are applied at others. When Pinatubo erupted in 1991, scientists from the Philippines worked with colleagues from the United States Geological Survey. The monitoring techniques, the eruption forecasting methods, the evacuation protocols, all were developed through international partnership. That knowledge is now available to observatories worldwide, including those monitoring Changbaishan. We learn from every eruption, every crisis, and the accumulated knowledge makes us better prepared for the next one. Second, technology continues to improve. Satellite monitoring now provides continuous coverage. INS, our interferometric synthetic aperture radar, can detect ground deformation measured in millimeters from space. Gas sensors are more sensitive. Seismic networks more comprehensive. We can see things now that were invisible a generation ago. We can detect changes earlier, process data faster, model outcomes more accurately. This doesn't eliminate uncertainty, but it narrows the window between warning and eruption. It gives authorities more time to act. It gives populations more time to evacuate. Every additional hour of warning can save thousands of lives. Third, there's growing recognition in China, in the international community, that volcanic risk is not hypothetical. It's real, and it requires sustained attention. Changbaishan is now monitored more comprehensively than at any time in its history. The network of instruments continues to expand. Research continues. Hazard assessments are updated regularly. This vigilance matters, because when the mountain does awaken, when the warning signs appear, the response will depend entirely on how well we've prepared during the quiet years. Preparation is everything. And preparation requires believing in risks we haven't experienced personally. There's also a broader lesson here, one that extends beyond Changbaishan, beyond volcanoes entirely. We live on a dynamic planet, a world shaped by forces that dwarf human capability: earthquakes, hurricanes, floods, volcanic eruptions. Climate change driven by processes too large and too slow for any individual to perceive directly. These forces don't care about borders, about political systems, about economies or ideologies. They operate according to physics, and they will continue operating long after human civilization has passed into history. Our only choice is how we respond. Whether we acknowledge these forces and prepare for them, or whether we ignore them until catastrophe arrives. Changbaishan is a test case, a relatively small challenge in the grand scheme of planetary processes, a single volcano in a remote region. Manageable if we choose to manage it. If we can't prepare adequately for Changbaishan, with all our technology, all our scientific understanding, all our resources, what hope do we have for the larger challenges facing humanity? Standing at the edge of Heaven Lake today, you see tranquility, water so blue it seems artificial. Mountains rising in the distance, forests clothing the lower slopes, birds wheeling overhead. The beauty is undeniable, real. But you also see, if you know how to look, the memory of violence, the caldera walls, the pumice deposits, the very existence of the lake in a depression that shouldn't be there. The mountain is both things simultaneously, beautiful and dangerous, life-giving and destructive. Past and present and future all compressed into a single landscape. This is the nature of our planet. This is the world we inhabit. The Earth is not a stage set, not a backdrop for human activity. It's an active participant in its own story. And sometimes on timescales we find difficult to comprehend. It reminds us of that fact with fire and ash and transformations that rewrite geography. Changbaishan will erupt again, the magma will rise, the gases will expand. The mountain will speak with a voice that carries across continents. When that day comes, we will be tested. Our monitoring systems, our emergency response, our ability to act on scientific information even when it contradicts our desire for normalcy. Some will heed the warnings. Some will evacuate. Some will survive because science gave them time, others perhaps will not. Because volcanic eruptions, for all our knowledge, remain fundamentally unpredictable in their exact timing. And humans remain fundamentally human, hopeful, stubborn, tied to place and memory and the illusion of permanence. But this is not a story about doom, it's a story about resilience, about the stubborn insistence of life, about forests that regrow on volcanic slopes, lakes that fill calderas, communities that rebuild, knowledge that accumulates generation after generation. The mountain destroyed itself in 946. And over 1,000 years, life returned. Water filled the void. Beauty emerged from catastrophe. This is the pattern. Destruction and renewal. Death and rebirth. The eternal cycle. The instruments continue their watch, the seismometers listen, the satellites observe. Scientists analyze data, build models, refine their understanding. And the mountain sleeps, breathing slowly, dreaming perhaps of fire. One day it will wake. And when it does, the world will remember for a brief moment in geological time that we are not the masters of this planet, we are guests. Temporary residents on a dynamic, powerful, beautiful, and ultimately indifferent Earth. The mountain has been here for millions of years. It will be here for millions more. We, in our brief span, can only watch, learn, prepare, and hope that when the moment comes, we've learned enough. Heaven Mountain, Changbaishan, Paektu. The mountain of many names. The mountain that should not exist, but does, and will, and reminds us in its silence of what it can be.